welcome to Atlas Press Metals and our first podcast here. I'm Mark Powell, Regional Sales Manager here at Atlas. To my right, Joe Finksler, Technical Sales Manager here at Atlas Press Metals. Joe's been here nearly 40 years now. And to his right, on the couch, Doug Haynes. Doug is our tooling manager as well as our new product development engineer. And Doug has, roughly 30 plus years of experience in powdered metal as well. We've kicked around names of this podcast, Joe, have we not?
We have, and I guess one has been settled on.
I guess we have settled on one. Maybe we didn't pick it, but our leader did, and we're going to go with what Ann said. We're going to call it the PM Blend. And welcome, and we appreciate you tuning in here on our very first episode of the PM Blend. Today we're going to focus on the compaction process in tooling, which is why we have our guest Doug Haynes with us this morning. So why don't we jump right into it, guys? Joe, let's talk a little bit about what compaction is.
Well, compaction is taking the powders, which are obviously loose when we start out, and interlocking them and creating a structure so that it can be moved to the next stage. So we start out with about 2 times the fill. So if you want a 1 inch long part, we start out with about 2 inches or 2.5 inches of powder and compact that down into a 1 inch long part at that point. That then allows us to move it on to the next stage.
Okay. And you can see down on the table here, we've got some samples of some different powders that are down below us there. So that is when he talks about powder, that's what it would look like there. So, Joe, how about what are the next steps, or what are the steps in the compaction process?
Well, you have to, the first step is obviously you have to load those tools into the press, and they would start out obviously empty. You then have to get the powder into it. So we have a fill shoe that comes across that will gravity feed that powder into the cavity. From there, the fill shoe retracts, the top punch seals off. At that point, then you're ready to do your compaction stage. In the compaction stage, the top and bottom punches will then come together at approximately the same speed, compacting the finished component, which is now locked down in the tool. The top punch will retract. The tools will then eject that part out, either by pushing it out or stripping the outside die away, to then create a finished component sitting on the top of the part. At that stage, then it's ready to be removed from the tool.
Okay. Doug, what components make up a typical tooling set?
Yeah, so Mark, the typical tool set's broken down into 2 categories. You have your perishable tooling, which is ultimately the most important tooling because that's the tooling that's going to touch powder. That's the tooling that's ultimately going to form that part. And then the second set would be your adaption. The adaption is, I don't want to say it's less important, but it's what adapts the tools into the press. It's what aligns the tools, bolts them into place. You would have like a backing plate that would potentially take that force, that compaction force, and it supports that punch. You would have risers that basically, set your punch length. And then on the perishable side, you would have, your die, your core rods, your punches. And once again, those are the more important ones because they're actually touching powder. They're actually forming the part.
And that those perishable tools are what you have in front, is that right?
Yeah. So we have a compacting die. We have some punches here, some different punches that you can see that, it has the profile of the part, and it's actually what's forming the finished part.
Okay. All right. So how does, Doug, compaction or tooling vary between simple and complex parts?
Yeah, so in a simple part, you'd have something that would have like a round ID, round OD. Design time is very, very short. Maybe take a day to design a set of tools for that, and the cost is very low, right? Because you have one upper punch, one lower punch, a die, and a core rod. When you get into some more complex parts, where you have splined ID, splined OD, multiple punch levels. Mm-hmm. You could have maybe one punch or two punches on the top, 3 or even 4 punches on the bottom, depending on the configuration of your press. You might have a satellite series of holes for lightning. Parts could be so complex that your driving the ID in from the top side. You could have step dies, stepped pins, a helical die. There's a lot of things that make a part more complex, and it ultimately, makes that lead time on that design a little bit longer. It could take up to a week for the design, and obviously that drives the cost up. The size of the tools, the number of tools that are in that die set could push the cost into the $30,000, $25,000 range.
And Doug alluded to an item there that I want to kind of point out. For the most part, most of our features on our tools are straight. The entire form is straight. But he just alluded to the fact that we have helicals. Mm-hmm. In that case, that's a little bit different set, because that actually, we're forming the helical gear form in the tools. So the portion of the tools, at least one portion, sometimes multiple portions of the tools, have to be able to turn during the mold and ejection stroke of that. So they're a little bit different circumstance. So it falls out of the we like everything straight mindset, and so it's a little bit different type of application.
Okay. Joe, what does it mean to manufacture parts to net shape or near net shape?
Well, it's pretty much what it sounds like. The objective for us, in the biggest bang for the buck for the customer, is if we can design and create a part that fits their needs, and we can form it without doing any secondary operations. Net. Near net just is nothing more than we've gotten a structure that's pretty darn close to what the customer needs, but we may have to do some secondary operations. It may need an undercut or a side hole drilled in it or tapped in it, something like that we have to do a secondary. But we try to get that part as close to that finished as we can, because that means the customer gets that finished part out of that single stroke.
We talk about net shape parts coming out of the press. Like what kind of cycle times is that? Like how many parts can we press an hour, Doug? What are we kind of looking at there?
It depends on the size of the part, the type of the press that you're in. If you're in a CNC press, it may be smaller, but you're looking anywhere 500, 600, 700 parts, right, Joe? Maybe even more. And sometimes you can do, a multi-cavity. You can mold 2 at one time, which improves your output as well.
Fastest presses would run in the neighborhood of, on a conventional press, 1,800 to 2,500 pieces an hour. High-speed presses can run 3,000, 3,500 pieces an hour.
Okay. All right. Tool life, Doug. Kind of talk about, again, we're talking about how many parts we can run per hour, but how about how many parts can we run a typical life of tooling?
So a lot of it depends on the part geometry, right? If you have a round OD part and you had a carbide die, you could get millions of parts from that die. If you have something that's like a gear with a very small corner radius, something along that lines, and if you're pressing that to a very high density, sometimes those tools could be prone to cracking. You might not get as much. You might get 100,000 to 500,000 range, but typically we're seeing in the millions. As far as the face details on the tools, they have to be redressed. You have very intricate chamfers and small little detail that will tend to chip out, but we end up putting about 3/4 of an inch on a punch for rework or redress, which we do here internally. We'll do that quite regularly as the chamfers chip out.
The other thing that will come into play of the tool life is also the tolerance that we're trying to hit. Traditional parts we do, the tools don't have any issues with that. There are some gearing applications that we do and some other structural applications that there's very tight tolerances to be held. Those are going to be more perishable, because that tight tolerance means I can't allow that tool to wear as far as we might in other applications. So Doug would see a situation where we on a AGMA level 6 or 7 gear that we may need to press that and replace that tool more frequently because of that tolerance.
Right, and in those applications where you have a high wear, there are certain materials that we can choose to help combat that. One would be like a carbide. There are certain coatings that you can do on tooling to help with wear. So there are things you can do to combat that. But Joe's right. There's some tight applications and tolerance applications that you have to take some certain precautions for.
Okay. We've talked a lot about tooling, but let's go back to the presses here a little bit. What kind of advancements, Doug, have you seen in compaction and the compaction process?
Well, in my 30 plus years, there's been a lot. There's been a lot of, I would say smaller ones. But for me personally, one of the bigger ones is the advancement of the CNC presses. They've been around, 20 plus years, don't get me wrong, but just the controls of them and the things that you can do with them. Joe had mentioned in the molding cycle, you have your fill, mold, and eject. That's on every single mechanical press, or every press you talk about. That's the cycle. Mm-hmm. With a CNC press, you can actually transfer powder before compacting it. So in between the fill process and the molding process, you can actually move material before you compact it. It lets you mold some very, very complex shapes. Some of the other things with a CNC press is contour filling. Or if you have a part that needs more fill in the front than the back, things of that nature, you can contour fill. And then the last would be the spring back capability. In bigger parts in a mechanical press, you have a lot of deflection between those levels, and you have to balance those in a mechanical press. Whereas in a CNC press, you can program that into the part and account for that deflection. So for me, it's the advancements of the CNC press and the controls.
Okay.
And to piggyback on that, the early CNC presses, you may have seen speeds of 100 to 400 pieces an hour out of them. They couldn't cycle quickly. Part of that was the controls. Part of that was the hydraulics or the systems that were used. And those improvements have now taken that and doubled and sometimes tripled the speeds you can run. Okay. And you're more precise in the positioning of the levels at that point as well, because the systems have gotten better and the controls have gotten better to read where they're placed. So that's another sidebar to that has really made that improvement. Okay. The other side of that, it would be the materials. The materials themselves have just made advances that have allowed us to press to higher densities, allow us to be more consistent. You don't see the dusting and problems that we used to see 40 years ago quite as readily today. So those changes in material have also advanced the compaction process.
Okay. Well, I'll throw this next question out to both of you because, Joe, you and I get this question oftentimes when we're out, whether we're doing a PM 101 or whatever we're offering together. How many presses do we have here? And
he's going to do this to us.
You always come back to me and say, well, Mark, what do we have? And, I throw out the number 35. I don't know if that's really true.
I don't know if that's. I don't know.
I know it's really close to that.
I tell you, I stopped counting at 30.
I know
it doesn't matter.
But
I mean,
let's give them a range of not only what we have, but tonnage that we can handle as well.
The tonnage is the smallest press we have is about a 15-ton press. We have one that's slightly smaller than that, but it's in that neighborhood. Most of those are fairly conventional presses. They've been in our building for years. Very reliable, very durable. Make parts that are down, the size of the tip of your pinky. We then jump into 30-ton, which doesn't make much bigger. You can get about inch diameter, 1.25 inches long parts out of that. Then you bump into the 60-ton and 100-ton. When we started, we had 15 and 30 tons up to 100 ton. So we've had that for decades. The more recent, as Doug alluded to, is our CNCs. That bump up 20 plus years ago, we got our first one of those. One of the originals that we had allowed us to do some multi-level applications. That was a 150 ton. And then we jumped into the 200 ton, and then we've gone into the 275 and 825. So we've gone from making parts that are very small to parts that are 9-10 inches across the cavity. So just to give a frame
some of those
reference.
big parts, I mean, they can weigh what, Doug?
2 or 3 pounds. Some of the ones we're doing.
Theoretically, we could be in the 5 to 10 pound range.
Sure.
Okay.
I think one of the calculations we did at one point, we could do up to a 15-pound part.
Right. In those new 825s.
In the new 825s.
Yeah, with the amount of fill that you have on there, you can get pretty big parts.
So a wide range of parts now that can be done here. So, okay. Well, listen, I want to thank you for watching our first podcast of the PM Blend. And if you like it, please subscribe to our socials.